In this video, we're going to introduce the idea of a proof just a little bit. And so we have postulates that we accept without proof, but most of our statements in an axiomatic system, like a geometry, are actually propositions, and propositions require proof. So we must prove propositions using the rules of logic. And one approach is to use a multi-column format. In this style of proof, the left column consists of statements or conclusions that we have established, and the right column consists of the justifications or reasons. So sometimes this is called a two-column proof, or I've seen it called a T proof. Sometimes we'll add another column that has the step numbers, and occasionally we'll add another column with illustrations. But at least this is a two-column proof. We will use column proofs written out in tables, and in my class we'll use Microsoft Word using, let's just use Word's equation editor to typeset mathematics and to do things like write line AB as AB with a line symbol over it and so forth. And so we'll insert certain symbols, mathematical symbols. And this will typeset appropriate mathematical notation as we do this. So that's one of the things I want us to get good at, is to communicating mathematics that way, so that as a mathematics practitioner or future educator, you can communicate mathematics very well on a piece of paper through a word processor. We will also provide illustrations, sometimes in the illustration column, sometimes other places, and these will preferably be dynamic illustrations that we build in GeoGebra, but we might include static illustrations in the Word file. So we will include links to the dynamic GeoGebra activities, which we will be able to access online, and static copies of those illustrations we can put in the Word file, perhaps in a step over here as we add things to the drawing. Now, geometry is a particularly nice area of mathematics to study because even though it is a form of pure mathematics, everything also has a physical illustration. However, illustrations, while useful and often required in homework sets, are not necessary for a valid proof. Proofs, in fact, should stand on their own without any reference to accompanying figures. One should be able to erase the figures and the proof should still make perfect sense. So you can't say, well, you see in the figure, no, that's not part of the proof. Each reason or justification given in a proof must be one or more of the following: something given in the hypothesis of the theorem, a previous statement in the proof, a previously proved theorem, a definition, a postulate, or some rule of logic. Those are the only things that can be used together. And typically we will start with something that is given in the hypothesis, and we'll always end with the statement, the conclusion of the theorem. Most theorems are if, hypothesis, then conclusion form. And so the if hypothesis, that hypothesis part is your first step, and the reason is this is given in the hypothesis. And conclusion of the theorem that we're trying to prove is the last step. And each statement in the proof is used as a reason later in the proof, otherwise it's not really necessary. Actually, one of two things happens. Either you used it later but didn't notate it, or you didn't really need it if you didn't actually use it later. So column form proofs are extremely useful format for learning how to write proofs. With a multi-column proof, it's easier to be sure that all steps, including the appropriate justifications, are present with no extra steps and that are included. As a pedagogical tool, multi-column proofs are excellent, and we will spend a considerable amount of time at the beginning of the course using this format. This is a good format to begin teaching the art of proof to secondary students, or college students for that matter. One good approach is to begin by outlining major steps of a longer proof and then going back to fill in the required details. In fact, this is also a good way to memorize a longer proof. Rather than trying to memorize every single step, memorize certain key points, and then hopefully you can go back and fill in the other portions as you go. So another good technique is to start working backwards from the end of the proof as well as working forward from the beginning, and hopefully you will meet somewhere at an appropriate place in the middle, and so then when it's reread from the beginning to the end, it makes sense. You should also employ the same basic type of writing process that is taught to you in your composition classes, where you make an outline, then a draft, and a rewrite, perhaps several times, before presenting your final proof. Don't just turn in a rough draft. As a mathematician and his or her audience matures, column proofs are abandoned in favor of a paragraph format. Since a paragraph format flows better, is easier to read, and takes up less space. The paragraph format is a more mature format and is more accepted for more advanced mathematicians. As the audience matures, more and more burden is typically placed upon the reader to supply the reasons for the steps in a proof, including deciding which earlier statements are referenced and when common basic results are applied. In fact, the first thing that usually goes is omitting the reference to where earlier in the proof the hypothesis was satisfied for the statement you're making. You're assuming that the advanced reader will be able to find those in the paragraph or paragraphs somewhere. Acceptable proofs for advanced mathematicians might only be considered sketches of proofs for beginning students. Many a graduate mathematics student cringes at the words clearly and obviously in a proof, since they are indications that some steps and/or justifications have been omitted, often requiring the student to provide paragraphs of work to fill in the missing steps. In this course, until notified otherwise, we will use a multi-column proof format with every step meticulously stated and justified and illustrated with dynamically constructed illustrations. Rules of logic. An axiomatic treatment of formal proof require the agreement of certain basic rules of logic. Here's a list of some of the basic rules of logic which we will employ in writing proofs. You should have encountered these in your Introduction to Discrete Mathematics class if you're in my geometry class, which serves as our first introduction to logic and proof for the mathematics major at UAFS. You should look carefully at truth tables for the rules of logic below if you've not already done so in a previous class. So first of all, what are allowed justifications in a proof? Notice that the reason given for a step of a proof in a multi-column format will typically identify a previously proved proposition or postulate, or maybe a definition, along with the step in which the hypothesis of that statement is satisfied. The statement we are justifying is then the conclusion of that postulate or proposition. The following are the only reasons that are allowed to be used as justifications in a step of a proof. Given by hypothesis is a reasonable reason, and we may use information given to be true in the hypothesis of the proposition, and that is typically the reason given for the first step in a proof. For example, if our proposition says we have a line, or maybe even more than one line in our geometry, then our first statement might be L is a line in the geometry, and the reason is it's given in the hypothesis. Most of the steps will say by step blank and postulate blank with a number put in there and perhaps the postulate written out. And we can use that as a legitimate reason as a proof, the postulate. So note that unless it's an existence postulate, the postulates are basically if-then statements. So the hypothesis of the postulate must have been satisfied in the previous step, which should be referenced. For example, here's a little piece of what might be a part of a proof down here, the start of a proof. Say we're in step 2 of a proof, and the reason or justification of step 2 is step 1 in postulate 5, then the hypothesis of postulate 5 must have been established in the statement of step 1, and then the statement of step 2 is then the conclusion of postulate 5. So suppose postulate 5 says every line contains at least 2 points. Another way to rewrite that is if L is a line, then there exist points A and B on line L. Okay, so if statement 1 is L is a line in the geometry, and perhaps the reason for that was given in the hypothesis, which again is usually the reason for the first step, then our second statement should be there exist points A and B on line L. Notice we can't use postulate 5 until we first have a line. Well, we have a line because statement 1 says that we have a statement 1 says that we have a line. So the hypothesis of postulate 5 is satisfied by statement 1, and so then we conclude the conclusion of postulate 5, which says there exist 2 points on that line, and we might as well give them some name. We might name them anything we want, but for example here I named them A and B. Notice that where we have a postulate, we have identified where in our proof we've established the hypothesis of that postulate, and then the statement here is the conclusion of that. Notice that the statement in one, or conclusion in one line becomes a reason or justification for part of the justification for a later statement. So every statement will be used as a justification later on, except for the very last one. And just about every line here is going to refer to a previous line as a part of the reason, except for the first one. We can do the same thing with propositions that we do with postulates, provided that proposition has been proved earlier. So by step blank and proposition blank is a reason that we could be using. We can use the previously proved propositions in the same way that we use the postulates. We use a previously proved proposition as justification for a conclusion if and only if we have established at an earlier step that the hypothesis of the proposition is true, and we have to be careful in ordering our propositions so that we avoid circular logic. We can only use propositions that we've already proved. So proofs of propositions can depend on earlier propositions in our list, but not itself, certainly, and not later ones as well, because that would get us into circular logic. Definitions can basically be used the same way. By step blank and definition of blank, we can use definitions of terms as justifications in either direction. Remember, either direction because they're if and only if statements. If we have earlier established that a geometric figure with a certain definition exists, then we can assume that it has the properties given a figure with that name in the definition. So in other words, if we know that it's a rectangle, and we know the definition of a rectangle, say, is that all the interior angles have the same measure, then we conclude that the interior angles have the same measure because it's a rectangle. On the other hand, if we can say that it's a quadrilateral with all 4 interior angles congruent, we know that's the definition of a rectangle, so then we can say our figure is a rectangle for our conclusion. Works in both directions. And finally, we can say by step blank and rule blank of logic, we can use rules of logic to justify conclusions. We can sometimes do a proof by contradiction. Sometimes at the very first part of geometry, a lot of our proofs are done this way. To prove a statement P implies Q, in other words, if P is true, then Q is true, assume that P is true, and we assume the negation of Q. Assume that our final statement's not true. Taking these together, we use our postulates and theorems and so forth to reach a contradiction, a statement that's both true and false. When we reach this contradiction, we know that the only thing that could be wrong is our assumption of the negation of Q, and so we know that Q is true, and we have P implies Q. Negation of P is denoted by tilde P, little squiggle P, and it has the opposite truth values as P. And notice that the negation of P is back to P again. If we have P implies Q and we want to negate that, that's equivalent to saying not P and not Q. And the negation of P and Q is equivalent to not P or not Q. And if you have for every x, S of x, some statement is true about x, then the negation of that is equivalent to there exists an x, at least one x, such that the negation of the S is true, where S of x is some statement about x. In other words, to establish that a universal statement is false, all we need to do is show that we have a single counterexample where the statement is false. We do not need to show that the condition is false for every example. For example, a function must pass the vertical line test so that every line touches the graph exactly once or not at all. All it takes to show that something is not a function is to find a single vertical line that intersects the function at more than one point. It does not require that we find more than one vertical line or that all vertical lines intersect the graph at more than one point. We just need a single counterexample. So a single counterexample is enough to establish that it's not a function. For a more geometric example, consider the statement, every line contains exactly 3 points. To see that this is false, we would need to find either a single line with fewer than 3 points, say maybe only 1 or only 2 points, or a single line with more than 3 points. That's 4 or more. The opposite of there exists an x such that S of x is true is equivalent to say for every x this is true. So that's just the backwards from what we just said, right? So if there's a statement that says there exists something that's true, then the negation of that is everything is false. If P implies Q and P are steps in a proof, then they can be used as a justification that Q is a valid conclusion, a step statement, or if P is a step in the proof and P implies Q is a postulate or previously proved proposition, or part of a definition for that matter, then we can conclude that Q is a valid conclusion. Here are some other things here. P implies Q and Q implies R is going to imply that P implies R. This is a transitivity property, right? Knowing P makes Q true, knowing Q makes R true, that means knowing P makes R happen. P and Q implies P tells us that P and Q, so if we know P and Q are both true, then P has to be true. Kind of obvious, right? Not Q implies not P is equivalent to say P implies Q. If P implies Q is the original statement, that not Q implies not P is called the contrapositive. For any statement P, the statement P or not P is certainly a valid statement. And that allows us to divide an argument up into cases too, something similar to that. Suppose we've already established that a sequence of statements S1 or S2 or up to Sn is true, and then in each case we argue that a statement C is true, then we conclude that the statement C is true. So if you can prove it in every single case, you've got it covered. Equality is our canonical example of an equivalence relation. Equivalence relations are symmetric, reflexive, and transitive. Reflexive means for every x, x is equal to itself. X is equal to x. If it's symmetric, that says if x equals y, then y equals x. It's transitive for every x, y, and z. If x is equal to y and y is equal to z, then x is equal to z. And we have a substitution property. If S of x is a true statement about x, and then y is an example of x, then S of y is true. Or x equals y, then we can substitute that in. Now, one thing that you have to, most of these I think are pretty straightforward and things you should know. Certainly most of you will be able to pick these up even if you've never seen this before. It's definitely useful to work out some of the truth tables for some of these if you've never done it before. But notice that all of these properties, or some of these properties at least, involve qualifiers. These qualifiers include things like at least, at most, exactly, and for all. Pay special attention to these qualifiers. For example, the statement, given two lines there exists blank point in their intersection. Okay. This has a completely different meaning if in the blank you put at least one, or you put at most one, or you put exactly one in the blank. Has a completely different meaning for the statement. So those qualifiers are important. However, if you just say there exists a point, that's exactly the same as saying there exists at least one point. Okay? In general, we have to be very precise and careful with the language of our statements in postulates, definitions, propositions, and proofs. Changing one word typically completely changes the statements. We do have some symbols that we can use. Okay. The negation of P is abbreviated squiggle P, like that. If P, then Q is abbreviated P, little arrow Q. IFF stands for if and only if. There exists an X is abbreviated with this symbol. There exists X. There exists a unique X is there exists and an exclamation point. That's it. There exists a unique X. P and Q is abbreviated by this caret symbol. P and Q. P or Q is abbreviated with that symbol basically upside down. Kind of like a V. And again, we're going to assume at some point in a previous course, if you spent some time carefully working through and justifying these and perhaps other rules of logic, if you haven't done so already, then you should work through some truth tables for the statements above to convince yourself that they are true.